So it's my great pleasure to welcome Anders Miltner. Anders did his PhD at Princeton, and he recently started a postdoc with Ishu Dilik at UT Austin. And Anders is very interested, doing very interesting things in the area of program synthesis and verification. So very excited for the talk. So Anders, please go ahead.
Great. Is everything viewable?
Yes.
I'm presenting. Okay.
Good. Yeah.
Hi. So I'm Anders, and I'm going to present my talk on the verification and synthesis for data structures. So first, let's just talk about data structures. They're a huge part of systems in software, particularly in large ones. They're really important. And a lot of the reasons that these data structures are important is because they can provide things like data persistence, and they can also provide mechanisms that restricts access to underlying data. So things like in Java, like private variables, and in ML family languages, things like module interfaces. But at the same time, there's actually relatively little work surrounding them. Why is this? Well, I think it's because it's pretty hard. Namely, the things that are useful in data structures are also what make it hard. So you've got data persistence, important aspect of data structures, but that means that you always have to ensure that the data structure stays safe throughout the entire computations. And you've got these mechanisms that restricts access to underlying data, but that means that sometimes the safety of the overall system can rely on how these data access restrictions happen. So it's difficult. And there are solutions. So namely, if you prove that a data structure can maintain a proper invariant, then that ensures that you solve kind of both of these problems. Invariants ensure safety over time, and they also ensure that, and the safety of the overall system can talk about these structures with assumptions of invariants being held. So in this talk, I'm going to talk about two systems, Hanoi and Burst. Hanoi is a tool for data structure verification, and it focuses on that task of invariant generation. Burst is a tool for data structure synthesis, and one of the key things is that it can synthesize recursive functions on data structures that can ensure the invariants are upheld. But before we get into that, I want to be clear on what I mean when I say data structure. In this talk, I'm going to talk about data structures in the purely functional settings. So functional modules, for those of you familiar with it. So for example, a set is one example. To be a set, you have to have some sort of underlying representation, which is a type T. And then you have some operations that operate on those underlying data. So for example, you've got an empty function, you've got an insert function, yada, yada, yada. And you also have maybe a specification on what it means to be a well-behaved set. So you've got like some sort of post condition describing, yeah, I really expect that if I look up an element in an empty set, I should return false. Or if I insert an element and then look it up, it should return true. So let's say I've implemented int set, and I've implemented it using an int list. That's great. Now I know that it satisfies all the functions, but I really need to ensure that it satisfies the post condition. This is where Hanoi comes in helpful. So let's say it's time to verify. We try to prove it, and we immediately hit an issue. Namely, if you do a lookup on a delete with the incoming set int list of 0, 0, deleting 0 from it and looking it up will actually return true. And that's due to our implementation. Namely, our delete removes the first occurrence. So is it wrong? I would say no, it isn't. And that's because in our insert function, we actually make sure that there's no duplicates. If it ever is the case that there would be a duplicate, we just don't add the second element to the list. Okay, so that means that 0, 0, while it is a valid int list, it isn't actually a valid set. It's not reachable using module operations. So how do we verify this? This is where invariants come into play. First, we need to find an invariant then you need to prove that the lists that satisfy the invariant satisfies the spec. And then lastly, you need to show that the invariant is inductive. So it's preserved over time. If you've done that, you're done. So first, when we're doing this, we find the invariant. In this case, it's going to be no duplicates. Next, we want to prove that the list that satisfy the invariant satisfy the spec. So we've got this spec, and then now with the invariants, we can add this additional assumption that on the incoming set, invariant is held. Then we have to prove that it's inductive. So what that means is that all of the produced values, all the produced sets must be maintain the invariant. So for empty, I just check that it's true. For insert, I can assume the invariant is held on the incoming set, and I need to prove that on the outgoing set, it's also held. And then I do that for all of the remaining functions in the module, and I'm done. So this step one of finding the invariant is a pretty key one. And this is where Hanoi comes into play. Hanoi takes as input a module interface, implementation, and specification, and will output such an invariant. And it does this with a relatively standard verifier and synthesizer communication. So what happens is we have a synthesizer that proposes candidate invariants to the verifier, and then the verifier will say yes or no, it is or is not a valid invariant. And if it isn't, it will return a counterexample. It performs this communication in the form of a test bed of positive and negative examples. So what the synthesizer takes in is this test bed, and it will spit out an invariant, and it ensures that the invariant returns true on every example in the positive examples, and it will return false on all the examples in the negative examples. The verifier takes in an invariant and then outputs a counterexample, which is then reintegrated into the test bed. So let's go into the full algorithm. You've got the test bed at the start. You send it to the synthesizer, which will give back a candidate invariant. And then you take the invariant in the specification and you check whether it ensures the spec. If it doesn't, you get a counterexample. And because it's a counterexample that doesn't satisfy the spec, you know it should be a negative counterexample. So like that 0, 0 example from before would be 1. If it's valid, then we send that and we check the inductiveness of the invariant. And we get a counterexample, which is either a positive or a negative counterexample. And then, or we can get valid and we're done. But this counterexample that can be positive or negative actually has some non-determinism. And it's a little bit the main kind of trickiness in this algorithm. So I'm going to go into an example of how these kind of occur. These are called inductiveness counterexamples. So let's say I've got a candidate invariant, which is the length of the list is less than 2. We know this isn't an invariant, but we'll see where things go wrong. So we check, is it held on just the empty list? And it is, so it's great. Now we go into insert and we find that it is not inductive. And we get a counterexample from our verifier. Our counterexample says, well, if you insert the singleton 1 or 0 into singleton 1, then you get 0, 1. Singleton 1 satisfies the invariant, but 0, 1 doesn't. But here's where the issue is. Is the issue that 1 is considered a valid representation of a set, but it shouldn't be, so it should be added to the negative examples? Or is 0, 1 actually a valid representation of a set, but it's called in this current candidate, it isn't, and so it should be added to the positive examples? This decision is kind of the key difficult. We need to decide, should we add 1 to the negatives or 0, 1 to the positives? We tame this ambiguity by adding an additional invariant to our algorithm. Namely, we say that all the positive examples must be constructible through module operations. So the positive examples we know must be true positives. With this in hand, we create a novel notion of visible inductiveness. Visible inductiveness asks the question, can we find an inductiveness counterexample where all the inputs have to be positive examples? So let's go back to our same candidate invariant. The length is less than 2. And the positive examples are empty list and singleton 1. I check the invariant and it's held on empty again. And I check on insert, and I find that it isn't. And now I get the same counterexample. Inserting 0 into singleton 1 gives 0, 1. But now I know that singleton 1 is constructible. So I know that 0, 1 can be safely added to the positive examples. And I know that it ensures our invariant because 1 was constructible and we performed module operations, 0, 1 also is. Now let's try visible inductiveness on a slightly looser constraint. The length is less than 3. We check on empty and it's ensured, and we check on insert and it also is. Because remember, our counterexamples can only be using the sets empty list and singleton 1. And then we find it actually is visibly inductive. But we do need to eventually ensure, is it fully inductive? So let's check, is it fully inductive? And then we find that it isn't on insert again. And that's because if we insert 2 into 0, 1, we get 2, 0, 1. So now, though, we know that we have to add 0, 1 to the negative set. Remember, we only can add things to the positive set that we know are constructible. We don't know if 0, 1 is constructible, so we don't know if 2, 0, 1 is. So that means it's totally safe to just add 0, 1 to the negative set. So now let's do our full out. We have to change our initial inductiveness check. Well, we first add the constraint that the positive set's always reachable. Then we change our inductiveness check to a visible inductiveness check. The counterexample, we always take the positive side of it. And because we potentially have incorrect negative examples, we use this as an opportunity to just clear them all out. After we ensure visible inductiveness, we do a full inductiveness check. In this counterexample, we always take the negative side. And if we get it valid, we're done. So if our verifier is sound incomplete, our synthesizer is sound incomplete, and our concrete data type only has a finite number of elements, then this algorithm will find a sufficient representation invariant if one exists. Now our tool Hanoi is our instantiation. Hanoi uses Myth as its underlying synthesizer. Myth is a type and example directed program synthesizer that can synthesize recursive functions. And namely, if you look at Myth, or if you look at our invariant, even something like no duplicates requires recursion. So having this recursive synthesizer is important. For our verifier, we use an enumerator tester, so not really a verifier. It's unsound, which is unfortunate for our theorems, but it's fast and it's guaranteed determining. So it works pretty well in practice. Furthermore, our theory doesn't address higher order functions, but our actual implementation does, and it achieves this with higher order contracts. We did some evaluation on this, and on a benchmark suite consisting of data structures from verified functional algorithms, which is a book, and the Cox standard library, and then also some other data structures we just thought were interesting. We ran it with a timeout of 30 minutes and inferred 22 of our 28 invariants. Furthermore, all of these invariants were correct, even though we used a tester, which was kind of nice. We compared against some existing techniques for solving this kind of issue of inductive specifications and checking invariants. They work on completely different domains, but we kind of just wanted to compare their way of handling inductiveness counterexamples. And we found that in our domain, visible inductiveness works pretty good. Okay, so that was the verification. Now let's talk about synthesis. So we've got this list set, and hey, now we also have an invariant, which is great. But data structures are often changing. You might realize, like, man, this really is annoying because I often do this insert all function where I have a list and I want to insert everything from that list into my set. I guess I could add in a fold every time I want to do it, but really I just want to change my definition of set to include insert all. So how do I do that? Well, I could just write it, or because we're PL researchers, we want to synthesize it. So what can I use for the synthesis? Well, I have the type of the set, and so I want to use that as well as maybe a specification of what it means to be a well-behaved insert all function, and use that for synthesis. in this one, what I'm saying and what it will be my running example is the size of the output is the size of the input set plus the size of the input list that I'm inserting all of after that list has been deduped. Okay, so we wanted to maintain this the invariant, and we want to have it maintain the post condition, so we can kind of integrate these two into a larger specification over the behavior. So for all the int lists and for all of the incoming sets, we want it to be the case that the outgoing set maintains the invariant, and it also maintains the size constraint. This is what Burst can handle. So Burst will take as input this logical specification, that's how I'm going to refer to those types of specs, and will output a function that will satisfy that spec. So there's actually already some existing work that can do this. Leon is some of the first, and then a lot of the benchmarks in the Cygus benchmark suite have kind of logical specifications, and then Synquid also can be used to solve logical specifications. But there's maybe some more stuff than just being able to handle logical specifications. We want to have recursion, and there's basically no Cygus solvers that handle recursion, but Leon and Synquid do. But we have some additional constraints. We really want to have non-inductive specifications. So we want our specifications to potentially just be kind of, these specifications involve these invariants, and these invariants aren't necessarily beautiful inductive invariants. It might just be something like, oh, the head of the list must be the smallest element, or something wonky like that. So we want to be able to handle these types of complex specs. So that takes out both Synquid and Leon. Furthermore, we want to have no top-down reason. Part of this is to handle non-inductive specs. By having top-down reasoning, a common approach is to do top-down reasoning is one of the ways that people handle these specifications, but it also kind of uses inductive specifications, as Nadia mentioned earlier, where you kind of come up with some idea about how you do the recursion. So that takes out Leon and Synquid. And then it takes out some of the Cygus benchmark or solvers, but there's also some that do top-down. But we see that there's nothing that kind of handles everything that we need. So let's get into our actual algorithm. As before, we use a communicating synthesizer and verifier, where the synthesizer will propose a candidate function f, and the verifier will propose a counterexample cx. In this talk, we're going to focus on the synthesizer. The verifier is relatively uninteresting, and also the outer loop, while it was really interesting in kind of invariant generation, the outer loop is pretty simple here. So what does the synthesizer take? Well, remember, we have these counterexamples, these concrete inputs of sets and inserted lists. And we also have our full logical specification. So what we can do is we can integrate these two into some sort of weird predicate. So this is like a predicate. Notice that we have an instantiation of the input list and the S. Now this is just a predicate on the output, saying, okay, well, valid outputs are ones that satisfy the invariant, and they also maintain the correct size. So in this case, it should have size 1. So that's great. That's one kind of type of specification. Our synthesizer can actually handle kind of Boolean formulas over these types of specs. This is called a ground formula, where we've got these kind of specialized formulas on given inputs. And this is what we're going to operate over in our synthesizer. Okay, so we've got these two needs of recursion with non-inductive specs and no top-down reasoning. For the sake of simplicity, let's just take out that non-inductive spec and do IO specs. So now we want recursion with inductive input-output examples, so trace complete examples, and no top-down reasoning. So there's actually some nice approaches that apply pretty directly in this limited form. Namely, there's this work on FTA synthesis. So FTAs are, or finite tree automata, are just some sort of automata structure. You can think of it maybe as like a generalization of DFAs. So DFAs can represent sets of strings. FTAs can represent sets of trees. Programs are trees. So FTAs can describe programs. And we want our FTAs, basically the language of them, to be the set of all valid programs. So here's one very complex FTA that describes kind of the input of 1 should go to 9. So we've got all these possible functions, but we find that if you take the input and then you add 2 or multiply 3 and then multiply 3 a second time, you get 9. So the 2 valid programs are like x plus 2 times 3 or x times 3 times 3. Okay, and the guarantee is that if we have in our input output example set, E goes to E prime, and we've constructed an FTA A from that, and F is in that FTA that we've constructed, then it will be the case that any sort of program accepted from that FTA will correctly transform the input to the output. There's some additional complexities about finitization, but that's just not going to. Okay, so that last task was described in the context of some numeric programs. Let's do it on this string, or this, list manipulating program. So let's do FTA synthesis where we've got these input-output examples. I'm going to focus on building the FTA just for 0 and 212 goes to 0, 1, 2. So we've got kind of our terminal nodes, or initial nodes, where, oh, if I have the input S, then it should return 0, or singleton 0, and then if we have I's, we have 2, 1, 2. So just to recap, if we have a tree that goes and ends in this 0, what that means is that we've got the program of, hey, let rec insert all of S and I's just equal S. And then because it ends at 0, that means that that function will return 0, that this insert all function. Okay, so we've got some operations we can do. We can extract, for example, the head of the I's and the tail of them. Okay, pretty cool. Now we have these sub elements. We can conv them together. So we've kind of got this loopy structure. And then we can do insert all. So now we're doing FTA synthesis with recursion. What should we return when we call insert all? In this case, we actually kind of have, we know what it should be. Because we know that 0, if we do insert all on 0 and 1, 2, it should be the case that it returns 0, 1, 2, just because we've got an input-output example saying that. So we can just say, okay, well, let's fill that in. And then this satisfies the spec. So we can say, okay, 0, 1, 2 is a final state. And so any accepting program is one, or any accepting program is one that ends at this final state. Okay, but we're not working over input-output examples. We're working over these ground specs. So I've got this ground spec for singleton 0 and 2, 1, 2, describing all this stuff about size and the invariant. I can start building the FTA in the same way. I extract the head, I do some conses, things like that. But eventually I'm going to have to call insert all. It's a recursive function that I need to synthesize. Well, what do? We only have our ground spec and maybe our logical spec. We don't have any like specification saying what 0 and 1, 2 insert all should do. Well, we just kind of add it. That's our approach. We add in all of the lists L, or it can go to all of the lists L, such that calling insert all with 0 and 1, 2 equals L, where that's consistent with the ground specification. So for example, we add in 0, 1, 3. It's consistent with the spec, so it's valid. We add in 1, 2, 3. We add in 0, 1, 2. We add in all these possible final states. And it's a lot. So this is our fundamental way of how we build up this FTA. Before, though, we had a meaning to our FTAs. Remember, we had a theorem saying like, oh, the FTAs exactly capture the correct programs. Now we don't really have that anymore. It's not the case that this is necessarily correct, our generated function. Is there any actual meaning to these FTAs? Well, yes. Now we can ensure that if we call, basically, if it is the case that a given output is consistent with the input, and f is in that accepted automaton, then it is the case that the function accepted by the automaton does evaluate to e prime under this new notion of angelic semantics. So basically it's saying it can evaluate there, but anytime you make a recursive call, you can just angelically decide on any possible of the outputs. So now we have a meaning to our FTAs. But we have a problem. We're over approximating. There are programs accepted in our automata that aren't necessarily accepted by, that aren't actual true solutions. So our solution to this is to perform a backtracking search. So say we've got our ground specification, chi. We want to first build an automaton for that represents all of the angelically correct programs. And then we get the A from that. So we extract one of those angelically correct programs, which is F. Now we check, does F actually satisfy the spec? And if it does, then we're great, it's done. If it doesn't, then we extract the assumptions that it made. So it extracts something like, oh, insert 0, 1, 2 should go to 0, 1, 2. We extract that as a another ground specification, phi, and then we retry synthesis, but we update our ground specification to be our original ground spec conjoined with our new var phi. If that then returns, then we're done. And if it doesn't, then we just negate those assumptions and retry with chi and negative phi. And if that works, then we're done. And if it doesn't, then there's no solution. Okay, we constructed a benchmark suite, or we kind of took a benchmark suite from the Myth and Smith benchmark suite, but then we added different types of post conditions to it. So we had example-based post conditions. We did a re-implementation post condition. So basically stating for all x, f of x equals reference implementation of x. And then we added in some logical specifications as well, things like those size constraints. We ran with a timeout of 2 minutes, and we were able to infer a lot of the programs for a lot of the benchmarks. So 43 out of 45 for the example-based ones, 43 out of 45 for the reference implementation, and 41 out of 45 for the logical. So that's Burst. It works pretty well. We have started working on another piece of work in this domain, which is full synthesis for the entire function or for the entire data structure. So adding in one at a time is pretty nice, but we really would like to just be able to give in like a module interface and specification and generate the implementation automatically. So I want to look at the post condition. These post conditions are kind of someone who looks closely can recognize this might be a relational specification. So it talks about the relationship between multiple different types of programs or multiple different programs. So relational spec, and there's actually some work that does synthesize functions from relational specs. And this is actually part of the motivation for why we said, hey, we want to synthesize bottom up. It helps with the grounds or the non-inductive specs, but it also is really helpful because by doing this, we can kind of plug into the relish approach and synthesize from relational specs. And it also can be used maybe as a plug and play in some sort of thing like Duet that is both top down and bottom up. So can we integrate this relational specification synthesis with recursive synthesis? And we found that, yeah, we kind of could. But when we did it, we did a very naive first approach, and it is very slow. So we're looking into ways of speeding it up. So in summary, data structure, verification, and synthesis is pretty important. Hanoi is able to find representation invariants, and visible inductiveness kind of helps tame ambiguity. And we synthesize functions that can respect the invariant with Burst. an angelic synthesis can help extend the prior approaches to work with logical specs. This work was done by my collaborators, Joshua Potty, Todd Milstein and Dave, helped with Hanoi, and Adrian Trejo Nunez, Anna Brendel, Swarat, and Ishel helped with Burst. So any questions?
I guess this is the, right, so this is the, thanks for the nice talk. Are there any questions, Peter? I guess, go ahead.
Yeah, thank you for a very nice talk. So I have a question about the verification or the
Yes.
generation of invariants for verification. So in my experience, data structure invariants are often more complicated in the sense that they need to be violated temporarily, and then you run into these reentrancy or callback issues potentially if you make a function call while an invariant is currently violated. On the other hand, you typically cannot forbid that because there are a couple of invariants where you have to make a function call in order to reestablish them after they got violated. So I'm wondering what your thoughts are on synthesizing such slightly more complicated invariants.
Yeah, great question. We actually talked about when me, Swar, and Ishel were kind of figuring out what we wanted to work on. This kind of was one of our ideas. Namely, like, could we maybe, what we were thinking was, could we do this sort of thing where maybe we have a temporal specification, where maybe you can say, it is, the data structure is valid, maybe not always, but if you have, but only under certain like operations. So if I do insert and then I do invalidate or something like that, then it would temporarily be bad, but after the invalidate call, it would be good. So we were thinking, oh, maybe we could do some sort of thing about adding in a temporal aspect. And we have not explored that, but I think that is an exciting idea.
So then what would you do currently if you had such a program? So say you have a doubly linked list, you swing one of the pointers, but not yet the other. So you have currently a violated invariant. So is your verification then unsound, for example?
No. So it would actually give a counterexample, or it would say that the data structure itself is not valid because we are saying it will always be the, so like if within the middle of a function it disobeys the invariant, that's fine. But if it's between function calls where you perform a function call and then you get to an unsound state and you need to perform another function call, it'll say, you know, you do not have a safe data structure. And that's accurate. It's unsafe under our current definition of safety, which is this very global idea that no matter what, anytime you are outside of a function call, you've got to be in the right state.
Okay, thank you.
And Felix, please.
Yeah, hi, thanks for the talk. I'm wondering about one of your examples in the beginning where you explained how you categorize positive and negative examples. Mm-hmm. And there you said, if I got it correctly, maybe I got this wrong, correct me if so. There you said if the functions of the module can produce the example, then you use it as a positive example, right?
Yes.
Yeah. So that means you assume the, you said this was Hanoi was a verifier, right? So do you assume the correctness of the implementation?
Yeah, I mean, so we're kind of like under the assumption, like, yeah, you're trying to verify something that's right. Fortunately, it is actually the case that if you have something wrong, it'll spit out, yeah, this is wrong. So what happens is when it finds something wrong, so it'll remember the positive set always has things that are constructible through module operations. So our criteria for terminating saying you have a bad implementation is basically whenever there is a element added to the positive example set that does not satisfy the specification, which means that then we are at the point where we're able to build up all these positive examples. But sorry, I lost my train of thought. We build up all this trace. So it's in the positive example set. So we actually have a trace of like operations that you've performed, and you also have a actual data structure that doesn't satisfy the post condition. So you can say, well, here's your counterexample. This trace of operations builds this bad thing.
Okay, makes sense. Thanks.
Any more questions? See, I guess it's getting a bit late.
Yeah, so
Yeah.
maybe Martin, let me ask.
Zhendong, yeah, go ahead.
Yeah. So Andrew's a nice talk. So I'm just trying to understand. So what do you envision as the way like you can practically utilize the work that you have done, right? So what's the
So right now we are really focusing on the purely functional data structures, and that is absolutely a limitation in terms of practicality because no one actually uses purely functional data structures. I do think that it can be kind of updated almost with very little work to work on stateful data programs. So like one very, very simple way is just reducing the stateful problem to the stateless problem, where we just kind of use like a state monad, but that's maybe less exciting. One thing we could do is add into our predicates a check about actual state in there. So we can do checks that use in the functional world, like reference, and can actually infer things when you can check references, and basically where you ensure not just on the output function, but also that kind of the references on all the inputs are maintained correctly.
Okay, so maybe a follow-up question is, Anders, how do you suppose you generate a function, and how do you guarantee the quality of the function, right? Maybe it's related to some
that's a
question
really good question. So yeah. So it is absolutely the case that the function could be pretty bad. Right now, the only kind of quality is that it satisfies the fact that it is sufficient to imply the spec and that it is invariant. Notice that, so the quality of the function is tightly related to the specification. So if your specification is just true, our invariants are going to be garbage. It'll just give true. One of the things that I personally thought would be kind of a nice seed would be some sort of thing that that maybe fuzzes a little bit, where it just kind of arbitrarily assigns some functions into the positive and negative set. And then it tries to build up like, oh, okay, we've got this positive set and we want to make sure that's good. But also we want to kind of, as much as possible, keep the negatives in the negative side to kind of make the specifications tighter. Because you want to have a tight specification. This is a fun idea, but we haven't yet done it. One additional answer to trying to get good values is subject to returning things that are sufficient to imply the spec. There is the nice benefit of a lot of synthesizers in that they have minimality guarantees. So you've got kind of these minimality guarantees that give you a bit of a Occam's razor principle, basically saying, oh, the simplest program is the right one, which actually does help a lot. Like I think that a lot of the programs are really generalizable and nice. The main issue comes from this sufficient to imply the spec, I would say.
Okay, thanks. Yeah, great.